All right, so this is the lecture 25, the very last module of the whole fall class and the real content class. So we will talk about unsupervised partitional clustering. And in this specific module 3, we will cover really quickly just a little bit about Gaussian mixture model. Okay, so let's get started. All right, so this is the roadmap, what we're going to talk about Gaussian mixture model.
Only cover the basic version here. Okay, so what is Gaussian mixture model? So for Gaussian mixture model, in the end, you're assuming each cluster are generated from a specific Gaussian distribution. So this is a Gaussian, this is another Gaussian, this is the third Gaussian, this is the fourth, this is the fifth. And we already learned, right, what makes a Gaussian distribution. A Gaussian distribution just needs to know the center and also needs to know the shape, the covariance matrix. And if you know the center, in this case it's mu sub j, so j from 1 to k. So it's very similar to k-means. So in the k-means case, you only need to calculate center, but in the Gaussian mixture model case, you need to calculate the covariance. That's the only thing actually more. There's actually a little bit more is we're going to talk about later. Is more than the k-means is it's not just about center, it's also about the shape. And the shape is represented by covariance matrix. Now, because of this, you can kind of reflect what k-mean really is about. In the k-means, we don't care sigma at all. And we only care about center. It has this implicit assumption is this Gaussian distribution is a rounded circle, or in the multidimensional case, it's a sphere. There's no kind of stretching or thinning type of shape at all. It's rounded. It's a round sphere. Okay, so now let's see what's Gaussian mixture model. And the basic method to train Gaussian mixture model is expectation-maximization. So you start guessing the centroid and covariance of each of the k cluster. So now your guessing is not just the center, you also need to guess the shape. And also beyond, you also need to guess the proportion of the cluster. So there may be dominating cluster, there are smaller clusters. You also need to have a parameter representing how did each cluster dominating the points. So maybe from the beginning you can just assume the probability of each cluster is uniform, 1 over k. Okay, so now you have this starting point, and similar to the k-means, for each point, you need to assign who is my cluster. It's very easy, and for each point, you try to calculate for that specific point, what proportion of my points belongs to cluster 1, cluster 2, until cluster k. And this is a very different step compared to the previous step. If you remember k-means, in the k-means, we try to estimate mij. I is for xi point. It's equals to 1 or 0, right? So if the xi belongs to the center j, it's 0, it's 1, otherwise. However, in the Gaussian mixture model, this mij is not a binary variable anymore. It becomes a proportion. It's trying to measure what proportion of the data points belongs to first cluster, second cluster, until the case cluster. After you doing the assignment, this is called a soft assignment. In the k-means, it's called a hard assignment. And in the Gaussian matrix model, it's called soft assignment. It's proportional. And after you're assigning the membership of each point to the clusters, and then you recalculate the mean and recalculate the variance, which almost the same as the k-means, you only recalculate the means. So let's use an example to show this. All right, so we start from this point located there. I'm just randomly guessing. There are two centers, and also the covariance is kind of rounded. So I'm guessing my cluster center exists here and there, and also they are very nicely a circle shape. Both clusters are circle shape. Okay, so now I'm trying to assigning all the points into the cluster. So you actually can, so roughly here, I don't show the proportion of each point to the different clusters, but just roughly, all the red points belongs to the red cluster, all the blue points belong completely to the blue cluster. And now you are re-estimating not just the center, but also the shape. And this gives you a very stretched out, very stretching type of oval shape, right? And this is the new red cluster, this is the new blue cluster, and then you recalculate the center and the shape, and then for that new center and shape, you're trying to assigning the membership again, until the end. The cluster estimates both the center and also the shape. So this is more than k-means because it measures the shape of the cluster. So this figure shows you the shape is also important. Okay, so this is one demo. I want to show you a different demo, which is actually a true Gaussian mixture model. Because the previous demo, each point, it seems to be completely belonging to the red or the blue, right? But in fact, the true calculation in Gaussian mixture model is you split each point to thinking how much that point is generated by the green cluster or the blue cluster or the red cluster. So this is the starting point. And you have a red cluster, which is kind of stretched out shape and has a really round oval shape. And the green cluster is nice, rounded green cluster. And the the blue cluster is even more stretched. It's even outside the whole page. It's very stretched out. And there are also this number called P equals to 1/3. Just trying to show you each cluster is the proportion. They are uniformly in the beginning. And now you're assigning each point into one of the three clusters softly. It's not hard. It's not yes or no. It's proportion. So you can actually tell the points, most points here, because it's actually very easy to check this. So when a Gaussian mixture model is so thin, it means what? When a Gaussian mixture model is so thin, we actually talk about it. Well, a Gaussian mixture model is so thin. So again, Gaussian mixture model, right? And that curve shows you in this direction is 2 sigma, right? This direction is 2 sigma. And we actually talk about it. Whenever it's more than 2 sigma, likelihood is 0, right? When it's outside the 2 in this direction, the thin direction, really, really narrow direction. So this direction is very centered. It's very, very centered around the center. Just a little bit off among the direction will be very unlikely. This makes what? It makes all the points here, of course, they're mostly belonging to the green cluster because this is so narrow. The blue is so narrow, and the red is also so narrow around that direction. So that's the reason why all the points here are mostly belong to the green circle, because that's the most likely. And then the points are more on this right side, and then it's difficult to know. It may belong to the green cluster, it may belong to the yellow, the red, or the blue. Okay, so now you assign each point softly into each cluster. Now you start to recalculate the new center and the new shape. And just after one round, your green cluster becomes more, there's a shape now. It's not a fully circled, fully rounded. It becomes more banded in that direction. And then the red circle becomes here, and the blue circle becomes a lot smaller. And then you're just reassigning all the points, again, based on the new center, new shape, and new proportion. You can tell the proportion also revised. So the blue one is 0.221. The red is, this is the red. Red is 0.27. And the green, I think, is about 51. So the green point is a dominating cluster. I mean, that number 3 number represents the ratio. And then you just keep doing again. And this gives you a much better density estimation about, so this is the proportion, and then you got, so until it reaches the stage, most of the points are dominated, controlled, generated by blue points, red points, and green points. And also there's a reason now you tell why this point belongs to the red, not belongs to the blue. Because, let's see, if using the K-means, this point will very clearly belong to the blue, right? But actually based on Gaussian mixture model, this point belongs to the red mostly, because in the end, that red cluster spreading over much more in this direction. So there's much more likely to generate the red versus this blue clusters. So it's capturing not just the center, but also the shape much better. All right, so just 2 minutes, Gaussian mixture model are very famously used for speaker audio analysis. This is the dominating method before the deep learning method. It's, if you know IBM speech recognizer, it's dominating the market before 2012 for almost 20 years. It's a simple method. You only just assume each speaker is a Gaussian mixture model. You calculate the mu, covariance, and also proportion. And then in fact, for each Gaussian mixture model, this is the parameter you need to estimate: proportion, center, and covariance. And then you have a total of K, maybe speakers. And then this is the whole thing you need to estimate. This is a much smaller and efficient model. And it's actually much smaller compared to the state-of-the-art deep learning models. But it's extremely effective and has solid performance in audio analysis. All right, I think that's it. Yeah, so this is the last page. Gaussian mixture model, mixture of Gaussian, and then actually what you're optimizing is likelihood. You check out the lecture about EM